Morning, everybody. How was the weekend? Yeah. Work, homework, all of the above. If I could drag you kicking and screaming into last Thursday, I kind of sort of started on this one and never really got there. So I figure we'll do this last example problem from chapter, whatever this is, 5, and then get started on chapter 6 today. You have an exam next week, right? Okay, so that's coming up pretty quick. This Friday and next Monday are both days off, so there will be no grasp this Friday, right? And I realized just now I neglected to look at tomorrow's lab. Tomorrow's lab should be lab 5, Newton's laws. Should be doing that. All right, we've taught, or at least I tried to teach you about Kepler's laws. There's 3 laws, 2 of them which are very conceptual in nature about the fact that real orbits are elliptical, and that there's like equal areas and equal times. A little bit esoteric, but we'll get into conservation of energy today. Kepler's 3rd law was that, I don't know, it looks kind of horrible, doesn't it? I mean, as far as physics equations go, right? It's this, right? Square root of g, big M, r to the 3 halves. And it's that r to the 3 halves that can throw people. But when we're talking about Kepler's 3rd law, right? This period, how long it takes something to orbit around something else. And what's that big M? What mass do we stick in there in general? The thing being orbited, right? So if we're talking about Proxima Centauri b here, right? That's the name of a planet. So we are in orbit around Proxima Centauri b, right? And so we're getting this orbital data about our spacecraft, right? We are in orbit around Proxima Centauri b, so it would be the mass of Proxima Centauri b that would go into that equation. The problem is here, though, okay, is we've got this amazing starship that can take us to Proxima Centauri b, but apparently it just can't tell us what the mass of Proxima Centauri b is. Right? So, right, we want to find the mass of Proxima Centauri b and then figure out what the weight of an object would be on the surface of that planet. So, knowing our orbital period, okay, and knowing how far we are from the center of the planet should be able to calculate the mass from this equation. It's going to require a little bit of square root, finagling and all that sort of stuff. But we should be able to get there. So first step, how do I solve that equation for mass? To get that big mass out of there. What's the thing that, like, if you got rid of it, it would make your life easier? Square roots, right? Okay. So how do we get rid of square roots? Square everything. So we're going to square both sides. We're going to square that side, and we're going to square that side. Okay, so left side I can do. All right. What's 2 squared? It's real early in the morning, isn't it? 2 squared is 4. Pi squared is pi squared. What's the square of the square root of gm? Well, that's just gm. Okay, and then what is r to the 3 halves squared?
3.
It's just 3, isn't it? Right? That squared gets rid of the 1/2 power from the r. So that kind of cleans up just a little bit. If I multiply both sides by the mass, I can cancel over there. If I divide both sides by the period squared, I can get that to cancel right there, and I'm left with the mass being 4 pi squared over big G period squared r cubed. And so now what's left is for me to go ahead and calculate that mass as 4 pi squared, big G, 6.67 times 10 to the minus 11. Ooh, this period. I've got to do something with this period. What's wrong with the period? It's in hours. What do we need to get it into? It's got to be in seconds, right? Standard units of time would be seconds. So a little bit of a sidelight here, 1.57 hours. And every 1 hour, there are 3,600 seconds right there. Let's see, did I do that? Yeah, 10,008 seconds. So 10,000 seconds. To a decent amount of sig figs, all right? And then I've got to square that. I got to remember to square that, right? So I got my 4 pi squared, I got my big G, I got my period squared, and then this R, I want to double check and make sure that this distance that we're putting in here, right, is the distance from the center of Proxima Centauri b to wherever our spaceship happens to be, right? This distance needs to be the center to center distance. Let's see, are they doing some weird thing like with altitude or so? Okay. They did tell me my altitude above the surface, right? 500 kilometers. But they also told me the total distance between our ship and the core is 7,500. So what number are we going to put in? We're going to put in the 7,500 kilometers, right? We got converted to meters. But we want the center to center distance, right? If they had told me the radius of the planet and the altitude, I would have had to add together. So always be checking to make sure, right? Make sure you understand if you've been given an altitude and a planet's radius or what have you. Usually when a problem says orbital radius, they say center to center distance. All right, so let's see here. 7,500 times 10 to the 3, and then I've got to cube that. And then the next step, of course, is to hope and pray that the calculator actually tells me the right thing. So we're all learning how badly our calculators can screw up these calculations. Parentheses in the wrong spot, and it just all goes wrong, right? But when I did this, I got 2.43 times 10 to the 23 kilograms for the mass. And so compared to Earth's mass is like 5.6 or something like that, times 10 to the 24 kilograms. So looks like Proxima Centauri b is potentially a Earth-like planet. Earth-like planets are things with about the same mass and size. I use the word about there very loosely. You're looking for a rocky planet. You're looking for something that's got decent gravitational acceleration at the surface. And this is certainly starting to look like a candidate here. Okay, so we found the mass. And now they're telling us the weight of an object on Earth, and we want to find the weight at Proxima Centauri b. So what's the thing that doesn't change no matter where we go? It's mass, right? The mass of an object is totally independent on whether gravity is pulling on it or not, right? So this suggests that we should probably try to find the mass of this object, and then once we have the mass of this object, try to calculate what the weight would be on the surface of Proxima Centauri b. So what does this look like? So part B, right? So if we know the weight on Earth is 560 newtons, and we also know that weight is equal to mass times little g, in this case little g on Earth, right? So I can divide by 9.8 here, right? Divide by little g on Earth, and I can get the mass of this object. Mass of this object turns out to be 57.1 kilograms. Okay, so now I have the mass, and if I'm going to find the weight on the surface of Proxima Centauri b, well, I've got the mass, but now I need to know the little g of Proxima Centauri b. Do we have something in our toolkit for finding little g on other planetary bodies? Yeah, we do. If I remember correctly, it was big G m over r squared. Did I get that right? I did. Big G m over r squared. That was the result we got when we were doing the International Space Station problem. And what big M is going to go into that equation? the one we found for Proxima Centauri b. If we want to know little g, right, on the surface of Proxima Centauri b, then I want to put in the mass of Proxima Centauri b, right? And then what are we going to put in for the distance? That r value. Where are we trying to find the weight of this object? On the planet. We know the mass of the planet, and we also know the distance from our spaceship to the center of the planet is 7,500, and we know we're 500 kilometers above the surface. So what's the radius of the planet? It's 7,000 kilometers, right? So there we had to do a little bit of subtraction to make sure we got the right one. So this is 6.67 times 10 to the minus 11. And then my mass that I found, 2.43 times 10 to the 23. All divided by 7,000 times 10 to the 3. Because I want little g on the surface. When I did that, I got 1.93 meters per second squared. Okay, so let's stop right there for just a second, okay? I just realized that my numbers are all off. I'm doing a different problem. Did I get the right binder? I did the right binder. For some reason, I've got like 2.78 hours for the orbital period. So that's a different problem. I suspect I know what happened here. Here it is. My apologies. I've been giving you the wrong numbers. This is what happens when you don't look real closely. So 1.57 hours is 5,667 seconds. You can go ahead and write hate mail right in the margins of your notes there. Mr. Balogh messed up my notes. This number is, I did it all correctly, I just didn't have the right data. 7.77 times 10 to the 24 kilograms, which puts it even closer to planet Earth. Okay, the 57.1 is correct for the mass of our object. Little g is not 1.93. That's what got me concerned there. 10.58, because I knew Proxima Centauri b had a much higher gravitational acceleration. Okay, now we're good. Yep. Now all the numbers on the screen are correct. Boy, it's a good Tuesday morning, isn't it? 10.58. How does that compare to our planet? It's really close, isn't it? Right? So, if you were standing on the surface of Proxima Centauri b, you would feel something very close to your own weight that you would say on planet Earth. Just a little bit more. Right? It's like, a tenth of a g more, which after a few hours you probably wouldn't notice. Your heart would have to work a little bit harder to pump blood through your body. It's just working against gravity a little bit harder, but again, this is totally within the range of our physiology to be able to adapt to. So the weight on the surface of Proxima Centauri b now is going to be the object's mass, 57.1, times our new gravitational acceleration. This turns out to be 604 newtons. Okay, so as you can see there, we went from 560 newtons to 604, so that's about 50 newtons, which is you're about 20 pounds heavier on the surface of Proxima Centauri b. So not a good place to go to lose weight. But, standing on the surface of Proxima Centauri b might be a little bit problematic, though. Subsequent data and analysis shows that it's probably a very hot planet. It's in orbit around a red dwarf, and this red dwarf is constantly throwing off solar flares, and it's close enough for this star to be bathed in the radiation of those solar flares. So though it is approximately Earth-like in the sense that its mass is okay, its acceleration is okay and all that, temperature-wise and in terms of finding liquid water on its surface, it's not a very good candidate. Okay, so our closest neighbor in the universe, not such a good second home. Yeah.
Why are you multiplying by 10 to the third of the denominator?
10 to the where?
To the third, and the gravitational force is approximately
For that mass up there?
at the very bottom.
7,000 times 10 to the 3 right here?
Yeah.
What's the radius that they gave me? 7,000 kilometers. Right? So how do you convert kilometers into meters? Multiply by 1,000. The kilo, that prefix literally means times 10 to the 3, right? So you can get straight into meters by doing that. I did exactly the same thing up here, right? 7,500 kilometers. Got to get that into meters. If it's not in meters, then your units aren't going to work out correctly. Good question. All right. That was the end of chapter 5. Always get the right binder when you're doing planetary science. Let's do a very rough segue into chapter 6. You have been through what students tell me over and over and over again is the hardest part of physics 2A. There's another little bump later where we're going to come back to Newton's laws and more dynamics and some more free body diagrams and things like that. But as your first time through all of these Newton's laws and free body diagrams and vector components and lots of big equations and lots of algebra, it's rough. That's a lot to swallow. Okay? Don't give up. Keep pushing through it. You're going to be okay. We take a little bit of a breather here. I mean, physics is hard all around, but the concept of energy and its conservation is something that just, you'll sense this later, it just feels better. It will flow a little bit better. And in fact, in physics, we generally will reach for energy before anything else. That's a little bit of a disclaimer. We haven't learned it yet, but when we get to simple harmonic motion is the first thing that we physicists reach for. If we don't understand something, okay, we'll turn it into a spring and see what happens. But energy and its conservation generally is a much less bitter pill to swallow. You only reach for Newton's laws when you're forced to. Okay? Not that they aren't important, not that they're not fundamental. It's just energy and its conservation, I don't know, just seems to feel better. And you might not agree with me after I'm done today, right? But let's see what happens, right? I'm trying to communicate to you that there's a little bit of a breather that happens here. Now, the problem with energy and its conservation and understanding it is that we don't have a really good definition of it, just like we don't have a good verbal definition for mass. Remember my analogy about how mass tastes like salt, right? You can't explain to me in words what salt tastes like, you experience it. Same thing with mass, right? You experience mass, but in terms of defining what it is, it gets a little bit problematic. Energy and mass are related to each other. And in that sense, it can be difficult to really... If I were to ask you what kinds of energy are out there, I think you can answer that. What kinds of energy are you familiar with? Heat, kinetic, solar energy, electrical energy, calories and things, right? There's just the types of energy, right, that we're familiar with in general, okay? But what energy actually is can be a little bit harder to pin down, which is why I like Paul Hewitt's definition. He teaches out at City College San Francisco, and he wrote a textbook for like introductory conceptual physics. It's not the textbook we use, it's for the Physical Science 11 students. But he said this, and I like this, right? I think this is the closest definition we're going to get to in words about what energy is. And there is this phrase that we use in talking about energy, and that's conservation. Now, I grew up in Santa Cruz. And if you haven't been to Santa Cruz and you don't know what Santa Cruz is, it's the place where the 1960s is still happening. Okay? Just haven't really let go of it. I grew up around tree huggers. I'm a tree hugger myself. Just environmentalism, go yay. But usually when you hear that term, conserve energy, it's about your parents yelling at you to turn off the lights, right? Or something like that. In physics, we have a very definite idea about what we mean by conservation of energy. Energy has these different types that you were talking about. But as far as we can tell, our universe has a set amount of energy in it. We can't make energy, we can't destroy energy. What we can do is convert that energy back and forth between types. Okay? Which is why I get a little bit upset whenever the popular media or people that I know or anything like that starts talking about an energy crisis. What's the energy crisis? When you hear about the energy crisis, what are they usually talking about?
Running low on resources.
Running low on resources, right? Running low on fossil fuels.
Running out of things that we can easily use to create electrical energy.
Okay, so it comes down to that right there, okay? But again, that's not an energy crisis. The amount of energy we have in the universe is set. We can't make more, we can't get less. What we have is an entropy crisis. And we'll talk more about entropy later, okay? It's the easy to use forms of energy. The types of energy that we generally use as a society here on planet Earth are not good for our planet. And so finding ways to get energy that also isn't going to make things really bad for us and our children and our grandchildren and our grandchildren's grandchildren is of paramount importance. We're going to laser focus in on this concept and idea as it deals with mechanics and how things move.
Is nuclear energy actually bad for the Earth? Because I hear both sides that like one part says it's not.
We're going to talk a lot more about this in Physics 2B, but for those of you that don't want to wait that long, and spoiler alert, I'll just give you the 2-second version, no. It's not bad for our planet. But it depends on what you mean by bad for the planet.
Destroys the environment.
Three-eyed fish, okay, and all that kind of stuff doesn't happen, right? Now there's Chernobyl, there's Fukushima, right? But here's the hot take, okay? By a factor of 10,000, so 10,000 times more people have died from the production of fossil fuel energy than nuclear energy. How much carbon does nuclear energy emit? 0. Nuclear is carbon neutral. It produces no carbon emissions, whereas coal and natural gas and all that sort of stuff do, right? So it kills less people and it doesn't produce carbon. Sign me up, right? Okay. If the NRC, the Nuclear Regulatory Commission, said that I could run a nuclear reactor in my backyard, I would do it. I would let my children kiss it, like it is safe. Okay. It goes wrong when you don't maintain things correctly, or you have really big earthquakes, right? Okay, those are the two cases where we've had things go wrong with nuclear energy. Otherwise, it's fine. It is expensive. Nuclear energy is very expensive to generate, and hence, people's electrical prices do go up. But it's a complicated answer to a simple question, right? Is nuclear dangerous? And in this physicist's opinion, no, it's not dangerous. And we should be using a whole lot more of it if we're really serious about getting off of carbon. Because right now we don't have a technology that can run 24/7 and produces no carbon. Like, I'm pro solar, pro wind, install treadmills in everybody's backyards and run on your treadmill to power your Xbox. I'm all for that, okay? But those things do not operate all the time.
I was looking for the guy that made a car apparently run on water, but you think that'd be impossible?
It's impossible. I mean, unless you pressurize the water, but then you're using a lot more energy than. I mean, I'd be interested, but usually these things end up being not what they say they are.
Does that just become a steam engine?
Yeah, it depends on what you mean by run on water. Because if you're doing electrolysis to separate the hydrogen and oxygen, sure, I can power a car, but you just use more energy to do the separation than you get out of motion. So yeah, it's kind of fun. Anyway, tangents. This is great. I love it. This is good questions, right? These are the things that naturally come up, right? Okay. But now we got to do what the state of California tells us to do and get back to the curriculum. I'm going to write down something very strange. And it's going to feel very strange at first because we're going to circle back around to it because we got to pick apart parts. But mathematically, we state conservation of energy like this. And the reason it's going to look strange is because you probably don't know what that WNC thing is over there on the left-hand side. Let's take a stab at the right-hand side first, though. What would EF be? Final energy, right? And energy initial? EI? So we're talking here about a change in energy, aren't we? Okay? Final minus initial. But I just told you that energy is always conserved, right? So what should the difference be between the final and initial energy? It should be zero. It just should be, okay? So what the heck's going on here, and why even have anything written down other than zero? So if I take this ball right here, okay, and I hold it, it's going to have something called potential energy, and we're going to get into this, but I want to give you kind of this overview of the thought process that's going on here. So this ball has potential energy. It's sitting in the Earth's gravitational field, and that gravitational field wants to cause the ball to go down, right? Okay? So we can say that let's just make up a number. It's got 10 units of potential energy, okay? And if I drop it, okay, it's going to trade that potential energy for something called kinetic energy, the energy of motion. And as long as there's nothing else going on, as this thing loses potential energy, it should gain kinetic energy. So if it has 10 units of potential energy with respect to the floor, how much kinetic energy will it have right before it hits the floor? It'll have 10, right? It'll have 10 units of energy everywhere. It's just a question of whether or not it's potential or whether or not it's kinetic. It loses potential and gains kinetic as it falls. But if I drop the ball, okay, well now it's at zero potential energy. And it's not moving. So how much kinetic energy does it have? Zero. I went from 10 to 0. I just broke conservation of energy. I started with some and now I ended with none. Where did the energy go? Somewhere else, right? Key, listen for it. You heard sound. Sound is a form of energy. Okay? The ball, you can't see it. We'd have to get the high-speed camera out, right? But the ball compresses, right? It's elastic. And so some of the energy goes into the compression and deformation of the ball. There's friction here. There's a lot of things that are going on that we are not going to be able to keep track of very well. Either because we don't understand how to do it yet, because we'll introduce it to you later, or we recognize that something's going on here, but we're going to throw it all sort of into a bin called non-conservative work. That's what that term over there, work NC, is. And I don't want to get too much into what is a conservative force and a non-conservative force. Basically, if it shows up on the right-hand side, it's conservative. Meaning that we understand what's going on with the form of energy that it is. WNC, that work done by non-conservative forces, is all the work that's done by things that we don't know how to deal with. Friction is the perfect example of a non-conservative force. Friction steals away energy. Now, when your car is moving at 60 miles an hour and you hit the brakes to come to a stop, you had kinetic energy, right? Where did all of that kinetic energy go? Into heat from the friction in your brakes. And for right now, and until the end of the semester, when we get to thermodynamics, we are going to not worry about that heat loss. We're just going to say that energy is lost to friction on the work non-conservative side. We recognize you can't create energy, you can't destroy it, but there are also situations where we don't really want to keep track of it. And so this statement right here encapsulates this idea. If there's no non-conservative work, if we can keep track of everything, then we're going to have this perfect conversion back and forth. But as soon as friction gets involved, as soon as somebody pushing something gets involved, as soon as a rocket motor gets involved, we are adding energy into a system. Sure, we're getting it from the fuel of the chemical reactions in the rocket fuel, right, are providing energy to get it to move. But we're not going to concern ourselves with all of those chemical interactions. We're just going to throw that into the work non-conservative side. I know this doesn't make a whole lot of sense right now. And my hope is that as we go along, it's going to start slotting into place for you. But I wanted you to get sort of this broad overview because I don't want you to think I'm a hypocrite saying, well, energy's always conserved, and then we start doing a whole bunch of problems where it looks like energy's not conserved, right? It's just that there are things going on that we don't want to get into the weeds about, and we're just going to handle it by saying, look, there will be a difference between what we start with and what we end with, but we can keep loose track of it as we go. All right, so let's start pulling this apart. We're going to tackle work and what that really means, and then we'll get into the types of energy that we have to deal with. Okay. Sucks to be them, right? Are they doing work? Well, the answer is it depends. This is a photograph, and so of necessity, it is an instant in time, right? It's an instant capture. These people could be pushing that van up the hill. Or they could be holding that van still from rolling down the hill. Or they could be about to be run over, right? And they're pushing up, but the van is rolling down the hill. It's kind of hard to say, right? From an instant in time. And the reason I show you this picture is because it underscores in the mechanical sense what work is. I know the word work comes heavily loaded for you, right? In terms of, well, that's the thing I do so that I can get money, so that I can pay for tuition and taxes, so that I can go to school, so I can make more money, so that I can pay taxes, and then all over and over again until I die, right? So we're not talking about that kind of work. We're talking about specifically mechanical work. And in order for mechanical work to happen, an object has to move. If an object does not move, no mechanical work has taken place. So if I sit here and I lean on the board, okay, am I doing any work? Many of you have taken biology. Some of you have taken anatomy and physiology. Are my muscles working right now? Am I expending chemical energy and supporting my body? Sure. But that's biology. In a mechanical sense, in a physics, mechanical motion sense, no work is being done here. In order for work to happen, there has to be a movement, okay? There has to be a force applied to an object, and that object has to move a distance d. And the way that we express that, well, in your book, okay? Okay, so I'm going to show you what your book does, and then I'm going to tell you why it's not great. I do that a lot here, don't I? Right? Argue with the book, and I know you guys hate it because you're like, oh, teachers, why do you pick the book then? It's not so much your book as it is the history, the historical inertia of why these things are written down the way they are. Oops. So work, very generally, is F cosine theta times S. I don't like this for a lot of reasons, okay? What's going on here? Let me see if I can't explain this and give you sort of a better way to think about it. Here's an object, okay? Let's say it's on the floor, okay? And we apply a force, okay, to it, and we move it a distance delta x, okay? So there the force and the displacement are in the same direction, and the work here would just be F times delta x. What happened to the cosine theta? That cosine theta is sitting there is the angle between the force and the displacement. In your book, they like to use S as sort of some generic displacement. I really don't like that symbology. So what's the angle between that force vector and that displacement vector? If they're pointed in the same direction. It's 0, right? And what's cosine of 0? 50-50 chance, right? Cosine of 0 is 1. Okay? Cosine of 0 is 1. Sine of 0 is 0. Right? And so if I do, I mean, you can see that it works there, right? Okay, because what's the big deal, Mr. Balogh? Okay, well, what's going on here? Work is trying to capture how is this force helping with the displacement of this object? So let me give you a different example. Here's that same object where, how do I want to do this? Let's say the force is being applied that way, but the object is moving backwards. You're like, what the heck? Why would that happen? Can you give me an example where you've got a force that's acting opposite the direction of motion? Friction! That's what friction, kinetic friction is, right? Which direction does kinetic friction act? Opposite the direction of motion. So what kind of work does kinetic friction do? If a force and a displacement in the same direction give me a positive work, what happens when the force and the displacement are opposite each other? Negative work? Oh, Mr. Balogh, my life just got a whole lot worse. Hold on.
Okay, so if you have like the friction, well, you're not showing the other forces.
Aha, yes, good. There are other forces here, aren't there? I mean, there's gotta be a normal force as it sits on the floor, doesn't it? Right? And all these are right? Work, okay? These aren't free body diagrams necessarily. I haven't shown all the forces that are acting on here, right? Okay? And I just sort of generically labeled that as a force. The point I'm trying to make here is that when we are looking at work, we have to be mindful of what direction something is moving and what direction the force we're trying to, determine is doing its thing. So this force, this work right here would be minus F delta X. And where did the minus sign come from? Well, what's the angle between those two forces? Sorry, between the force and the displacement? Not 0. It's 180 degrees, right? 180 degrees is the way we say things are opposite each other. And what's the cosine of 180? It's -1. Okay, what about a force that acts perpendicular to the direction? And now this displacement can be either way, okay? How much work does that force do?
It canceled out.
Doesn't cancel out. What's the angle between that force and the displacement? It's 90 degrees. What's the cosine of 90? 0. How much work is that force doing? 0. Can you name a vertically acting force? This is a normal force, right? And so if we were to look at all of the forces acting on an object, say, that is being pulled across the surface of this desk, right? There'd be the force that's pulling it, doing positive work. There'd be the force of friction, doing negative work. There'd be normal force doing no work, and there'd be gravity doing no work. We could add up that total sum of work, right? But the reason you're seeing that cosine theta in there is because there is a dependence on which direction forces are being applied and the direction things are moving. So what happens if you get a situation, say, where the force is being applied at 50 degrees above the horizontal, but the object is moving horizontally? What angle do you put in now? You put in 50, okay? Usually, you're just gonna see, like, your book will do it, I will do it, okay? Where we won't write down the cosine theta. We'll just say it's positive work, negative work, or 0 work. There, what we've done is we have already looked at what the angle is and be done with it. Part of the problem with this approach, and this is kind of how your book did it, and I wanted to teach you that way the first time, but let me give you a cheat code for all of this, okay? Just pick the component of the force that points in the same direction as the displacement. I'm not sure why physics textbooks always choose to do it this way, but they tend to ignore all of the skill that you just learned in Newton's laws, and then they just throw equations at you and say, good luck figuring out the angles. F cosine theta. What is F? In this drawing that I made up here, this F has an X and a Y component, doesn't it? And what is F cosine theta? It's this one right here, right? So why not just say, pick the component of the force that points in the same direction as the displacement. You're done. Because sometimes angles aren't given to you nicely. We know this now, right? The angles can be given from vertical axes and all that kind of stuff, right? So that's what's happened here. That F cosine theta is really just saying, well, if the displacement is in the x direction, we'll use cosine, right? What if this displacement were vertical? We'd need F sine theta, wouldn't we? And then you'd come to me, the book says cosine theta, but in the homework I had to use sine. I just wish they would teach you to use the components. You know how to find components, right? And why not Why not just use that anyway? But from this we learn that work can be positive, negative, or zero. Okay? So if I drop this ball, is the work done by gravity positive or negative? Think about it. Just stop and think. What direction is gravity pointing? Down. What direction is the ball going? What kind of work is this? It's positive work. Don't worry about, oh, down's negative. All that matters is that displacement and force were in the same direction. Okay. As I pick the ball up off the floor and I lift it up, am I doing positive or negative work? Ooh, very good. Why was it negative? Well, actually you did it wrong. Which way am I pointing? Pushing the ball. Up. Which way is it going? I am doing positive work. See that? Okay. What is doing negative work? Gravity. Which way is gravity pointed? Down. Which way is the ball moving? Up. Right? So I'm doing positive work on the ball. Gravity is doing negative work on the ball. How much work am I doing on the ball right now? Zero. But Mr. Balogh, it's moving. Okay. Which way am I applying force? Up, right? I'm supporting the ball's weight. Which way is the ball moving? Sideways. That's zero mechanical work done by my force. Now the friction between the ball and my hand is doing work. Okay? In this case, static friction. Right? And static friction, is it doing positive or negative work? Say that louder. It's positive. Why is static friction doing positive work in this case? Static friction is what's making this thing go to the right. Kinetic friction, though, what can we count on? Kinetic friction always acts opposite the direction of motion. So what kind of work will kinetic friction always do? Negative work. All right. Let's see how you're doing with a quiz. All right. Blitzkrieg through the kinds of energy and their mathematical definitions, because what I want to do is I want to bring this all back and start doing some examples. I might run out of time. I don't know. We'll see. We'll see how far we get with doing all of this. Okay. Kinetic energy. What's kinetic? Juan.
Real quick, just to clarify, so the distance and the weight is still going to be considered.
Yeah, because work is force times distance. I did sidelight. I did neglect to talk about the units of work. Right? And I usually write work like this as a shortcut. What happened to my cosine theta? I'm just going to pull the component of force off that I need, okay? And for distance, I just use d. Sometimes delta x, but never s. Anyway, what are the units of force? Newtons, right? And what are the units of distance? Meters. This is given a new name called the joule. Not like diamonds, but Joule, James Prescott Joule. We use the symbol J for it, okay? And that's the unit for work. Because work, non-conservative, and energy end up in an equation together. You want to take a little stab at what the units of energy are going to be? Also joules, right? A joule equals a joule minus a joule. Right? You can't mix units when you're specifying things like that, right? So the joule, okay, is a unit for both work and energy. And so it gets a little bit even more confusing sometimes about like which one is which. Like if I have a certain number of joules, what's going on here, Mr. Bailey? The joule as a unit is something that you are probably totally unfamiliar with. And if I have to be honest, I'm not really familiar with it that much either. Like if somebody told me this thing is using 10,000 joules of energy, I'd be like, so, right? It's much more useful as a comparison, right? If I know something's using 10,000 joules of energy and another thing is using 100,000 joules of energy, well now I know that there's a factor of 10 difference, right? So it's not the actual numbers that are as important as like what the differences are and the comparisons and things like that. It's just, we are more, so the unit of energy you are probably most familiar with, and it's something we're not gonna get to the very end of the semester, is the calorie. You've heard of calories before? If you've been for more than like 3 nanoseconds in the United States of America, you've taught to count calories, okay? So the calorie is a unit of energy that's contained in food, right? That our bodies can then use to do other things, right? Okay? But the calorie is basically 4.2 joules. Not that that helped you either. Okay. Here. It is the unit and we will use it, but again, it's comparisons that are more important than knowing what the actual number is. Alright, kinetic energy. So that was a bit of a sidebar there because I forgot to do that. Kinetic energy. Kinetic means what? Means moving, okay? And so, without proof, because you probably don't care that I prove it to you, we can write down the kinetic energy of any object if we know its mass and how fast it's going. Exactly how many vectors are on the screen right now? 0. I haven't even bothered to put vector signs above the forces, right? And the displacements. Work is a scalar. Energy is a scalar. It's a half lie because you kind of do need to know like the direction of the force and the displacement to be able to do the work correctly, okay? But the vector hat is off today, right? They're there, they're lurking behind the scenes. But one of the nice things about energy is that it is a number. It doesn't have direction associated with it. That V in there is the speed. I just need to know how fast something is going. And if it's not going, how much kinetic energy does it have? 0, right? So we can, once more, we can look at the motion of something. Back in Newton's laws, it's like confusing. It's like the change in motion. Like what does that even mean, Mr. Balogh, right? But now we can just look. Is it moving? Yes, it has kinetic energy. How much? Well, it depends on its mass and how fast it's going, right? Interestingly here, though, what happens if you double the speed of an object? If your car is going 10 miles an hour, but then you speed it up to go 20 miles an hour, how much more kinetic energy does it have? If the speed goes to twice the speed, then the kinetic energy is equal to 1/2 times m times 2v quantity squared. What happens to the 2? Becomes a 4, right? Okay? So this becomes 4 times 1/2 mv squared, doesn't it? I square the 2v, which means I square the 2 and I square the v. And I end up with how much more kinetic energy? 4 times. Thank you, I was being very awkward in my grammar there. A doubling of speed is an increase in 4 for the kinetic energy. What happens if you triple the speed of an object? It's 9 times more energy. So how much more energy do your car's brakes have to dissipate if you've doubled the speed? 4 times the amount of energy. That's how kinetic energy works. It's the square of the velocity. All right. So that's the mathematical form that we will use for the energy of things that are moving. We then have potential energy. And by potential, we very much mean that like this energy is stored in something. Just like you have the potential to do amazing things in this world with your life, it's not happening now. I mean, you're amazing. You're doing amazing things right now. but you get the idea of what I'm saying here, right? The potential, so we're gonna actually define different kinds of potential energy for the rest of the semester, just depending on what we run into and things like that. Kinetic energy is just objects in motion, but potential energy can be stored in the gravitational field, in a spring, in a rubber band, in the wiggles between molecules in a chemical substance, in the nucleus of the atom. There's lots of places where potential energy can be stored. Okay? And we're gonna keep adding to this list. But for right now, we are going to be defining potential energy as m times little g times h. Now this one I can kind of tell you where it comes from. What's mg? That's gravity pulling on things, right? Okay? So if I take this ball, right, and I move it up a height h above the ground, gravity wants to do work on it, doesn't it? How much force is gravity applying on this ball? mg, isn't it? And what distance does gravity want to make it go? Down, right, through a height h. Force times distance, right, is the amount of work. So mgh is the amount of work that gravity could do on this ball if it were free to go. So that's why work and energy very much feel like the same thing sometimes. What we're recognizing here with potential energy is that that energy is stored. The work can happen, it may not happen, but it's stored, and we know what amount it's going to be because we know how much work is going to take place in order to get it. The other amazing thing about this statement here is that it doesn't care about what's happening sideways. In other words, the amount of work that gravity can do on this ball is totally independent on whether I drop it or I throw it sideways. If I throw it from the same height, then the amount of work that gravity does is just mgh. It's the vertical height that matters. So even though something might be dropped, again, height is this distance above the ground. It's a scalar, it's not really a direction. We're not into like, oh, do I have to remember if delta y is negative? No, you don't. It's just a number. It's fantastic. It's so good. It's so good. Okay. So that's, and this is potential energy gravitational if I really wanted to be specific, but for now we'll just leave the symbol as potential energy. If for some reason, this does happen every once in a while, I use the symbol capital U. This might slip out. This is the standard symbol we use in physics for potential energy. But your book uses capital PE. So I'll try to stick with what your book does here. The symbol doesn't matter that much, but I was trained many years to use the symbol U, and I still use it. Still squeaks out every once and a while. I'm curious to know if this is going to work. Did we have trouble within this class? It was like playing really fast. Yeah. Let's see if I fixed it. It works just fine at my desk. It's just this room.
Raising a mass
it's working.
increases its gravitational potential energy.
I fixed it.
We'll use this triple track to show that this energy is conserved as it changes from one form to another. We'll release a rubber ball
Does he
down
look like
each
he
of
enjoys
these
his
three
job?
tracks. Each track has a similar downhill section, but the uphill sides have different slopes. If a ball is released from the top of each track, how high will it rise on the other side in each case?
All right, so 3 tracks. They're all connected at the same end up there, right? It's going to roll it down so it goes up the steep one, and then the middle one, and then the long one. How high, which one of those is going to have the ball raise higher, do you think? Why would it be the same, Jay? They all look the same? I mean, they're all different different like angles, aren't they? Yeah, but they all go to the same height and the ball all starts at the same height, right? So energy has to be conserved? Let's see what.
Here's the ball rolling down the first track.
Okay, thank you for the graphic. Okay, your job's on the line. If you don't do this right, careful. Careful.
The second track.
Okay. No smiling. This is science. No smiling. Why is he being so careful? Doesn't want to give it any
The third
initial
track.
kinetic energy.
The ball rises to the same height from which it was released in each case.
Good job, no smiling. Serious science stuff, right? So why did it all go to the same height? It all started with the same amount of energy, right? Gravity, potential energy, it doesn't care, right, about what the path looks like. If there's no non-conservative work, if there's no friction happening, and there the ball was rolling, we'll get into what rolling means later, okay? In this case, there's no kinetic friction to act against it. It's all going to roll exactly to the same point. All right, that's enough for today. We will reconvene tomorrow for lab, and we're going to do more free body diagrams and Newton's laws, because who doesn't like doing that? And then we'll get back into energy on Thursday.